They're going live
So
here
we
now.
haven't gone live yet, so as soon as so, not to keep the people online waiting. So, John, you, so yeah, we can start now. Yeah.
1 second.
Here. Morning, ladies and gentlemen, and to everyone else who might not necessarily see themselves fitting into that category, myself included. My name is John Harrison from Southwest College, and I've had the pleasure of being project lead for a renewable engine over the last 4 years. I'm happy to greet you all and welcome you on behalf of the organisations. I was going to say welcome you all to the Merchant Hotel, and I got that one wrong because that's where we were about half an hour ago. But glad to be here now. We had a hot fitted up. And I may forget the rest of this welcome speech because that's all it's about. The Merchant Hotel, as you may know, is formerly a bank. And that's where I wanted to start off and say, it was very nice of Interreg 5A to support us in funding the project. I'd like to welcome a warm. Sorry, just talk. Had a bit of a panic attack there, so John, you?
Yeah, Matt. Morning, everyone. My name is John Bartlett. I'm Head of Research in the Sligo campus of the Atlantic Technological University Designate. That's a mouthful. Okay. Used to be IT Sligo, still are IT Sligo, but on the first year it will be the Atlantic Technological University. I'll come back to that. Let's call that an arc. We'll be coming back to that at the end of what I'm saying. It's 38 years this year since I got my first environmental qualification. 38 years. And when I got it, people said to me, that's the up and coming thing. Environment, that's great, that's the up and coming thing. And every year since then, they've said, that's great, that's the up and coming thing, you know. Having said that, I do think we're starting to get traction eventually. It might be under climate crisis stuff, but we're getting traction eventually. That is because that was a progenitor of renewable engine. The reason that we stayed together and put in the application for a renewable engine was because the CREST project was so successful. And this is an opportunity to shout out to SEUPB as well, because with CREST, research wasn't part of their portfolio previously. So they took a bit of a leap of faith with us, with CREST, in funding that first project. And then, of course, in 5A, in the most recent pillar, it is a full-on pillar, and that's fantastic, and we've been successful in that. So what we've done in Renewable Engine, the key difference over that engagement model was bringing postgraduate students into industry, either SMEs or MMEs, and building the research and innovation capacity and ambition of those companies, and solving problems and developing new technologies as well. But the real new piece, the real key enabling piece, is putting those students directly with the companies. So it's been a fantastic experience, and again, Peter and John and I and others have been talking for the last few months now about where we go next. This group is not going anywhere. We're going to develop this platform vertically and horizontally. There'll be a lot more coming down the line. But it's been a fantastic experience. And the companies that are here, some will be speaking for themselves later on, will give their side of the thing. But from my point of view, in higher education, it's been brilliant working with these companies, working with SEUPB in funding this. But at the end of the day, for me, the key players here are the students. And the work that the students have done, the experience that they've gained, and what they're taking out now into their professional lives as a different way of working between academia and industry and social groups as well. So I'm delighted to have been involved with this. Thank you all for the opportunity, and looking forward to hearing what everybody else has to say this morning. Thank you, folks.
Thanks, John. Sorry about earlier there. I thought I was going to faint there. Probably running around. I'll be given a sweet bun, so I think I'm better now. Yeah, I'd just like to welcome our next speaker. It's Jitendra from Queen's University.
So he's going to
Jitendra online.
Yeah.
The video.
Yeah.
So this is going to be a video presentation of his work at Queen's University.
Hello everyone, this is Jitendra. I'm working with Dr. Peter Martin and Dr. Gary Martin. My project title is Advanced Simulation of the Rotational Molding Process. I'm currently in the fourth year of my research studies. I'm developing a simulation model which will help me determine the better process variables. The outcomes of the project are improved quality of the product, better process design, and improved productivity. This is the overall view of the presentation. Rotational molding process is simple process manufacturing thermoplastic products which are essentially stress-free and economically manufactured. Process involves charging the mold with a predetermined quantity of polymer powder, subjected to simultaneous heating and two perpendicular axes of rotation. Once the polymer gets stuck to the mold wall, it is moved on cooling chamber where it is sufficiently solidified and demolded. Molds can be broadly categorized into concave, convex, and irregular, with shrinkage and warpage depends on demolding temperature and cooling rate. Whenever there is a non-uniform cooling on either side of the part wall, this introduces large temperature gradient and subsequently thermal stresses. As a resultant, part wall gets detached away from the mold wall. This introduces air gap formation between the part wall and the mold wall, which acts as an insulator. This further delays the cooling time required. Thermal coefficient of expansion approach is adopted for the simulation of shrinkage and warpage. That is, for every degree change in temperature of polymer shrinks by a certain value. Deformation plots shown here are for the case of air-cooled parts. In the case of rapid external cooling, the heat transfer coefficient ratio of external surface to the internal surface is 10:1. And in case of rapid internal cooling, it is 1:10. In both the cases, as expected, part wall bends away from the mold wall. Deflection graphs shown here are a set of points selected on the surface which has a maximum deflection, plotted over span of the cooling cycle. Maximum deflection is observed in the case of rapid external cooling case. The important positive impacts of the project will be the right set of process parameters, information time is saved. This in turn reduces the cost of molding cycle. Material repurposing becomes efficient by checking its molding feasibility for the designed product, everything before mold going to full-scale production. Excessive usage of energy is cut down, which is another saving carrying out simulation work. Rectification of possible molding shortcomings leads to better product and hence profit to the molding company. All of the above advantages makes optimum molding possible. At the moment, there are no simulation models for warpage prediction in rotational molding. This study will try to fulfill that gap. The experimental trial for better mold be removed or greatly reduced. Rotational molding industry's 4.4 plan will be complemented by this work. The simulation data few plots shown here is in good agreement with the experimental results. It can be used to analyze different grades of material or altogether for a different material in processing conditions.
Jitendra, not sure if you're online, but yes, thank you very much for that interesting presentation. A lot of it was over my head, but I think that's the nature of, I suppose, what we try to do with Renewable Engine was kind of to blend the higher level academic research that's required with industry who can actually take those research outputs and make commercial use of them. So thank you very much, Jitendra. That's the first of our academic presentations. Next up, I'd like to welcome Chris from Kingspan, and he's one of our industry partners who's engaged on the project, and he's going to explain the work that they've been undertaking with Queen's University and the rest of the Renewable Engine program. Thanks, Chris.
Thank you, John. Thank you for net zero carbon. Again, we want to make all of our products going forward net zero carbon. Very simple. Sounds simple, isn't. Circular materials, so that will feed into net zero carbon. So trying to increase our recycled material into any products. Renewable energy on site. As I mentioned, the first program that we had, the first 10-year program, our aim is to increase all of our manufacturing processes to use at least 60% renewable energy. If any of you have been to our Portadown site, you'll see solar PV that we have on the roof, you'll see CHP plant, so we are trying to maximize that, and that is one of the core features of this project. Okay, and the last one, conserve water. Again, we're just trying to reduce our water usage across the board. So that brings us on to the project rationale. So as I mentioned, our current portfolio on the energy side, oil and diesel heavy. So we wanted to diversify into zero or low carbon energy storage. Hence, hydrogen for us has become a key player in that space. We believe customers that we already service will be looking at it as a replacement rather than electrification. It will be in its place, not instead of electrification. They will both have a role to play, and we want to be a world leader in supplying that solution. So net zero carbon rotational molding process. Jitendra gave you kind of a basics of what rotational molding is, and if any of you are not aware, it's effectively a big old oven which you heat with natural gas. Really, really not environmentally friendly, and we want to get to a place whereby we can get net zero manufacturing in that space. So third part, explore Industry 4.0 technology. Again, that comes from a need that going forward, CNC machining has become, has increased its capabilities, meaning that the designs that we are now receiving into our factory are becoming more and more complex, and therefore we need processes that can deal with that from simulation through to process control, heating zones, etc. So that's the rationale. What we did on this project then, working with Queen's, and Alex is down front, did a lot of the work for us. So we designed and prototyped a polymer liner for hydrogen storage. So that's the first element of a hydrogen storage vessel, is the polymer liner that will hold the gas in. We wanted to assess the manufacturability of new processes. So Queen's have a AMS rubber molding machine, which is effectively a robotic arm which you put the mold on, and it can control heating zones across your mold. I'll show you a picture later on. Therefore negating the need for natural gas, therefore making net zero carbon if you use renewable energy. Hence we solved one of our problems. And then the third part was to develop the market understanding. So where did we want to go, who did we want to sell us to, and all the needs that were required. So the first phase of that, which took a lot longer than we probably all anticipated, was the design. And the reason it took so long seems reasonable enough. Which companies, sectors and geographies need this, will be requiring it, will put it into use. Which actually isn't as simple as it seems. As I say, electrification has its place, as will hydrogen, and trying to balance out where that's going to fit was a tricky understanding. Competitors, so what competitors are out there, who's doing what are they doing, what's the industry norm around size, scale, etc. Regulations, probably the biggest sticking point because there are no harmonized standards. polymer tanks that were made with a different polymer, and we couldn't get to work at that point. But we did end up with some really nice tanks that you'd happily send on to the next phase of testing. So we did that. We took them on to testing, and I haven't shown you again gas heated ones that we made over in our site in Willerton, because again, you don't want to see pictures of the dirty factory. It's not as cool as Oregon. So I'm not going to talk you through the numbers because you get bored. But basically, I just wanted to put this up. What we do have is a 3D scanning arm. So we wanted to compare the molds, the moldings that we got with the CAD file and see, did we make what we set out to? And really the take home was, at this point, with the time we had and the optimization limits that we had, that there was no benefit to using the new fancy piece of kit at Queen's. It was basically the same. So that wasn't to be disheartened, because what we're saying is this, at this moment in time, the conventional one is probably optimized to as much as it can go, and it is not fit for purpose. It would not meet the quality standards we would like to get to. What we do know, though, is the AMS robot mold and any electrically heated tool can be optimized. We probably touched on about 5% of what the system could do. But at this point, they're about the same. Therefore, there we go, thank you, Rob. Where to next? So I suppose really, that was a quick scan through to what are we actually going to do and what is the impact of this research. So using all of that knowledge, I was able to take it and present it to Kingspan senior management and said, look guys, we really need to push on with this and invest. And that's what we're planning to do. So next stage is to optimize the liner, the manufacturing process, and say we've probably got 95% optimization we can do. We've got pressurizing the tank we can do. We can do a couple of cool things that we designed into the mold. We then need to produce a full Type 4 tank ready for testing. So that includes carbon fiber winding and all the extra little bits. And then what we have done already is we've got to a point internally whereby this project has allowed us to go, as soon as we're at prototype and we get testing, we will be investing to fully to go into full production. So really the impact of the renewable engine has been, we will make these once we get there. So thank you very much. Are there any questions? That was a very quick run through, so apologies.
Chris, did you find, in terms of corporate culture, did you find having a postgraduate student team working with your full-time staff disruptive in a positive way or a negative way?
No, to be honest, and again, I'll try not to link too much to COVID, but due to COVID, having Alex and having a full-time resource at disposal meant that we could do this project. If we hadn't had Alex, we wouldn't be at the point we were at. This probably wouldn't have got past the first couple of design stage meetings internally, because all of our resource has been diverted into dealing with supply chain issues and everything else that comes at the moment with COVID. So yes, having that resource and having the ability to go to Queen's, I was annoying Alex and Mark up at Queen's regularly, pushing them on. So, but having that resource to actually go, just get it done, it made the project happen rather than it would have just fallen down otherwise.
Higher level stuff, and you see then how that can feed down into processes and actually deliver an end product. And that's what, again, Renewable Engine was all about, that kind of practical research. So it's very good to see that, and useful to see there when you're going, okay, well, we did this and didn't work, or it looked to be the same as the old process. Well, right, just spent a load of money and a lot of time, but that's the nature of research. I think people take their learning, and then the upside is there is more upside. So yeah, very interesting. Okay, next up we have again, this is two presentations. One from Sean O'Connor and another one from Stan Matthew, both from IT Sligo. Are they going to roll back to back?
Yes.
Yeah. Okay.
Hello everyone. For those who don't know me, my name is Sean O'Connor and I'm a PhD student studying at the Institute of Technology Sligo. So for the Renewable Engine team, apologies that I'm not able to meet in person, but hopefully this recording can give you a better understanding of my research to date. Whereas in investigating the role of small-scale anaerobic digestion platforms in furthering the development of an Irish circular economy. So to kick off, I suppose what really drew me to this research was number one, my undergraduate degree in sustainable energy engineering, and number two, coming from an agriculture background myself, where I could see that Ireland has consistently struggled to meet its climate change obligations, with one of the main contributors to this being the country's large agriculture sector, which has consistently accounted for nearly a third of total emissions produced. And the large part of why this sector produces so much greenhouse gas emissions is due to its large livestock population. But obviously it would be difficult to just simply reduce this herd size because of the damaging social and economic costs. So we need to find alternative solutions. So this really brings us to my research topic. So of all the renewable technologies available, anaerobic digestion is uniquely suited, especially for the agriculture and food sectors, as it is capable of reducing greenhouse gas emissions while also producing renewable energy. But despite these benefits, the technology has seen little uptake, with much of the research to date focused on large-scale systems, which often don't suit Ireland's farming structures. So to address these challenges, this research aims to first evaluate the current status of small-scale anaerobic digestion, and then implement relevant improvement strategies and technologies. So in the next two slides, I'm just going to briefly touch on two of the main objectives of this research. So the kick-off, the first element of this research was to address the societal impact of farm-scale anaerobic digestion plants, where it's important to understand the general opinions, willingness to adopt and perceived obstacles of potential adopters of the technology. So to do this, we surveyed Irish cattle farmers to get a better understanding of their motivations. So you can see some of the key findings from this study on screen. So number one there, the study found that 41% of the 91 respondents were interested in installing EV on their farms within the next 5 years. So the second bullet point there shows that the results indicate that the main considerations preventing the uptake of anaerobic digestion was a lack of information regarding the technology, and B, the potentially high investment costs involved. So the third one there was that of the likely adopters and the possible adopters, 58% of them expressed an interest in joining a cooperative scheme, while a self-owned, self-operated and self-owned ownership model was the preferred structure. And so I suppose the key insights that we came away with this was that there is willingness and there is support for the adoption of anaerobic digestion on Irish farms, but there are still many challenges that need to be overcome. The main one is just a general lack of awareness of the technology, and the second one being that the high investment costs involved in actually installing this technology at the moment. So the second element of this research aimed to assess the viability of small-scale anaerobic digestion plants while modelling the technical, economic and environmental considerations of operating such plants in Ireland. To do this, we developed a model that simulated the integration of an AD plant on dairy farms with various herd sizes. This ranged from 50 cattle all the way to 250 cows. So you can see some of the results on screen there, where The first one there states that the feedstock quantities available on farm were sufficient to meet the farm's energy needs, with surplus energy exported, which could represent 73 to 79% of the total energy generated. Moving on to the second one, where the study also found that AD systems were profitable within the plant's lifespan on farms with a herd size of upwards of 100 cattle. And this had payback periods ranging from 8 to 13 years. So overall, the main insight found from this study was that AD systems were economically sustainable method of mitigating greenhouse gas emissions on Irish agriculture. So as previously mentioned, this research also looked at various improvement strategies in assisting the acceleration of the adoption of AD plants. So one improvement strategy research included attempting to reduce the high fixed costs associated with traditional AD systems. This is by designing and testing a modular anaerobic digestion plant. So to do this, we were collaborating with an industrial partner called Organic Power to design and optimize a demonstration scale system, which was tested in the AFBI Institute located in Hillsborough in Northern Ireland. So I suppose the main advantage of this system is that it's number one, robust, number two, cost effective, and it's number three, highly mobile, where it is designed to operate inside two standard 40-foot shipping containers. So this system is still under its testing phase, where Organic Power hope to have it commercially ready very soon. So I suppose in summary, this research aims to accelerate the adoption of anaerobic digestion in Ireland by number one, evaluating the technology's current status, and then implementing relevant improvement strategies and technologies, which included a modular design and a decision support tool. So looking forward, it is hoped that this research findings will guide researchers, policymakers and AD operators in furthering the development of an Irish bioenergy industry. And lastly, I would like to say a massive thank you to the whole Renewable Engine team, especially my supervisors, and lastly to the funders for supporting me over the last 4 years with this project. So for those who would like to ask any questions or to get in touch, my email address is shown on screen, and I'm happy to answer any questions.
Hi everyone, my name is Neha Matthew. I'm a PhD research student in nanotechnology and bioengineering research group in Institute of Technology, Sligo, Ireland. So here I'm going to be talking about my project. So as part of Renewable Engine program, my project overview is to develop high temperature stable and visible light active photocatalyst for antimicrobial and energy applications. So here basically we are trying to make a material that can harvest light energy. So let's say from solar light or room light or LED light, and that can induce the production of reactive oxygen species on this material. So this produced reactive oxygen species can go and react with antimicrobials to kill them completely, or same reactive oxygen species can react with water to split the water into hydrogen and oxygen, just to apply an energy applications. So in this project we use a process called photocatalysis. So photocatalysis, it means that it's any chemical reaction that can be enhanced using use of light. Photo means light. So here basically we are working with a material called titanium dioxide. So titanium dioxide is a widely used semiconductor material. So but the main limitations used for the titanium to use in particular visible light active photocatalysis. That's to harvest light and visible light energy was because of wide band gap. So the energy levels between the conduction band and valence band in this material is pretty high, so it can only get active under UV light. So that was one of the major limitations, and another was that titanium dioxide have different structural phases. So anatase, rutile, and brookite. In among these, anatase is have more active phase, and it is not um, thermally stable at a high at a high elevated temperatures. So these are the main two limitations that we had with titanium dioxide. So here we dop titanium dioxide with an element. Like the doping means we're introducing any foreign elements to it as an impurity to increase its property. So this was the main process we used in this project. My industrial partner is Castos. Castos is an antimicrobial coating company based in Dublin. So they're mainly focusing on surface coatings to prevent antimicrobial and antiviral infections on the mobile phone surfaces, laptop screen, and test surface, etc. So with the collaboration with the Castos, our main aim was to produce like material that can be activated by room light and which is very highly temperature stable. Means that it can also have a high reactive phase that we can have, and this also can be used for tiles and for the coatings because they are annealed at a very high temperature to build the process. And we also were looking for enhanced antimicrobial activity. So if we can use these materials that can be active under the room light, so that will be good enough to use all this as antimicrobial coatings even inside our rooms. So we have worked with different elements during in this project to how to modify titanium dioxide. We have worked with a variety of materials. So one of the results was we dropped sulfur, selenium, tellurium into titanium dioxide, and we checked what's the effect of these elements in titanium dioxide. So we found that among those elements, tellurium showed 100% disinfection of E. coli within 17 minutes of irradiation. When we are testing in the dark conditions and light conditions as well. So during dark conditions, there was no change or no death of antimicrobial for microbials. But with the effect of light and by the introduction of tellurium, it shows within 17 minutes of radiations, there was 100% of disinfection of E. coli. And this material was also was stable at around 750 degrees Celsius. And another study we did with copper. So in copper, we introduced a minor fraction of copper in the titanium dioxide. So even with this introduction of copper, we tested with dark and light conditions of and tested the antibacterial activity of copper for two strains, E. coli and S. aureus. So here also we found that even within much quicker 30 minutes of radiation, we have a 99.999% of bacterial death. So in this project we introduced with different dopants in titanium dioxide, and we checked the activity of antimicrobial and we tested. And so along the process, we also collaborating with Castos, we got around 9 publications in high impact journal journals. So in overall in this project, we have developed materials that we can have a solar light energy and can be effectively used to kill E. coli and stuff even with light, with room light or solar light energy. Thank you for listening.
Just before we move on, just maybe one notable aspect of renewable energy is the 12 postgraduate engineers that were put into industry. 50% of them were women. It's very unusual and very common.
Well, many thanks for the two presentations. I did have a question or two to ask there, but then if you're doing it on video, it's kind of hard to do that, so we'll leave that one. I suppose the one question I picked up on was everybody might want to know on the microbial action of copper. Does that apply to COVID as well as the E. coli? As you would probably expect.
There's an antiviral surface thing that they were working on, yes.
Very interesting. That's not renewable energy, but you know.
But that's the point, John. You see, renewable energy, renewable engine as a project has motivated other people to get into this space and has been the progenitor for a whole lot of other projects as well. So, you know, it's the power of the group is special.
Yeah, very good. Okay, so next up, let's just check our time. We're a wee bit ahead of schedule, but I don't think anyone's ever brought that up as an issue previously. It's only when you run over. I'd like to welcome David Surplus from B9 Energy. David's going to present on the research that he's undertaken with themselves and Queen's University and Mansouri. I should note now Mansouri has moved on. She's now with the University of Cardiff in a KTP position working with industry. So well done, Mansouri. That's very exciting for her. David.
Okay, thank you, John. Hello, everybody. Yep, my name's David Surplus. Been working for a couple of years now on the renewable engine supported research. We had already begun some work with Horizon 2020, and we found that there was ways in which renewable engine could complement that and fill some gaps and actually help us at the end of that project just to continue on for a little while. So the first slide here is where we started all of this, which is a problem that occurs on electrical distribution networks. The oval circle is an area of County Down called Blackwell, just to the southeast of Downpatrick. The blue lines are the 33,000 volt distribution network heading the power down into that area. And in the middle is the substation, where you have a reduction in the voltage from 33 to 11,000 volts. And the bright red lines are the 11 kV circuits, you know, going down to farms and buildings around. And that was designed and built in the 1950s. It's designed for one-way flow of current from the central power station through all those lines and ending up in houses. But what's happened, of course, recently is that we've started to embed some generation. We've got solar panels connecting onto those 11 kV lines. We've got single small wind turbines as well. The AD projects that you saw before would connect on to 11 kV. And in the case of Lakehill, we also had the Queen's University CGen, the tidal mill in the Strangford Narrows. So what that then does is if you get enough local generation on that 11 kV network that it exceeds the available load, then you get the current trying to go the wrong way and moving up into the 33 kV network. The transformer's not designed for that. It would need to be replaced, big bucks to do that. So the idea of putting a compressed air energy storage project at the substation in the middle there is to absorb that energy locally so that it doesn't have to go back up in. So what we did was design a control system that would look at all of those environmental conditions and decide when to either put a load on the grid, i.e. compress the air, or to put generation back onto the grid, which is when you expand the air. So you're holding compressed air in the storage receiver. What the system is an internal controller, which has the compressor and the expander that it can start and stop. Next, please. And connected to that is an external controller, which is the brains of the system. And it's going to be saying when these things are stopping and starting, depending on what all of the external conditions are over there. And in order to make sure we have a good plan for the day ahead, then there's a day ahead simulator with predictive algorithms. And it has all of the inputs about tomorrow, what sort of temperatures are going to be, what's the usage pattern on a typical day at that time of year, what's the wind and solar forecast like, etc. So it's that green bit in the middle that we wanted Renewable Engine to help us with. Next, please. And we designed and built a simulator on a software platform. And if you step through these are just the parts of that system, showing the elements of the control system. It's an Amazon Web Services core, and we got all of the ability to do that through the program. There's two more here just to bring up, and you can even get all of this information on your mobile phone. So that was a very useful tool. And what we then did was to get some historical data going back for 12 months period prior to that. And we ran the simulator as a hindcaster, and we then put in place what would have happened last year, whenever we would operate this system. The next slide shows the 12 months in the year and a series of revenue streams. Each color is a different revenue stream for a different service that we're offering to different clients at different times of day for different reasons. They're either local or distant, fixed or variable. And what we found was that mostly the income is coming from putting a load onto the grid rather than generating onto the grid, which was a surprise. We didn't expect to see that. It's only about 15% comes from energy trading. So we realized that load was more important than generation, and thought that we should look at a better way of applying load. So next, please. But before we completed our work on the compressed air energy storage, we built a machine that uses water hydraulics to move what's called a liquid piston. This is the problem when you compress air, you generate a lot of heat, and if you don't capture that heat, then you become very inefficient. And so what we want to do is capture the heat and store it, and then when we expand the air later on in the day, we've got the heat to stop the system from freezing. So that thermal storage allows you to approximate isothermal compressed air energy storage, so the same temperature. And it's a holy grail. A lot of teams around the world working on this. This was the rig that we put together for trying to do the experiments on the heat exchanging in order to be able to capture that heat. And the next slide shows the apparatus that we constructed. That last diagram sort of on the screen there. It's pumps, compressors, valves, storage tanks, plumbing, it's straightforward enough stuff. The active bit is where the two men are, that vertical structure, and the next slide just explains that a little bit, where there is a cylinder with a piston inside it and a slug of water sitting on top of the piston, and hanging from the roof of the cylinder there is the heat exchange elements. And what we're going to do is move that piston up along with the column of water and then submerge those elements at the top. So as the thing is moving up, the air is compressing, getting warm, the heat goes into the elements, and then when they become submerged, the heat goes into the water. And all of that is mounted in that rig there. And the next one shows we actually had two cylinders. The top cylinder was fixed and the bottom piston was fixed, and we had a mobile piece that could move up and down. And the next little bit there just shows each one has got an element of water in it, and that just shuttles up and down. So they're mutually exclusive. It's either one or the other, which is operational. So the whole sequence is done by a shuttle valve going A or B. So it's quite a neat little arrangement. And Mansouri Kaljani from Iran did all of the work for the CFD, computational fluid dynamics, the thermodynamics and the fluid mechanics as well. She simulated it all on a software program. And then the testing that we did was there to verify all of that computational work. And then, of course, once you've validated the model, you can then begin to condense years worth of trial and error into simulation work on a computer. And this is the system, of course, which we had. We had nighttime wind in particular, daytime solar feeding into the compressed air system. We were offering demand-side unit grid balancing services to reduce curtailment of wind farms and other local generation. And the only output from that was electricity. And that's good, but it avoids the need to upgrade the substations, and it's got a few other benefits, but it's not as good as when we then moved on to the next piece. If you get the next one, please. Which is to replace the compressed air energy storage unit with a high pressure electrolyzer. So cold because it produces hydrogen gas at 35 bars, so you don't need to compress it to get to what is a reasonably good pressure. An electrolyzer is a machine that just carries out electrolysis. You put water in. For every ton of hydrogen you get out, you have to put 9 tons of water in. So therefore you get 8 tons of oxygen produced as well. And this shows you what you can do with what we call power to X. So power is coming in and you're bringing out not just electricity, but X, lots of different things. On the hydrogen side, you can use that green hydrogen, which of course is called green if you've used renewable energy to drive the machine, into hydrogen pipelines, either discrete, 100% hydrogen pipelines, and they are in the Ruhrgebiet and in southern Texas and places already, or you can blend the hydrogen into the natural gas networks up to and including 100%, although you do need, when you get above 20 volume percent, to convert the appliances at people's houses and businesses. So you can use it directly, you can synthesize it with CO2, preferably green CO2, either the stuff that's been scrubbed out of biogas at AD plants, or direct air capture of CO2 from the atmosphere, or indeed you can capture it from seawater. Blend the, catalytically react the CO2 with green hydrogen, you get green methanol, and that can be used as a renewable feedstock for plastic synthesis, for example, or direct use as a fuel. You can then take 2 methanols and join them together to give you dimethyl ether, which is a very useful drop-in liquid fuel because it has a cetane number. So it will ignite under pressure and can be put into diesel engines. So it's another step, but you know, Queen's is actually looking at combining a lot of these steps into one single reactor. Quite interesting stuff, and it's a transition fuel which says, let's make use of all of those vehicles that are out there today and get them substituted. And in the future, when they're at the end of their life, you replace them with pure hydrogen ones. The oxygen, we, right from the outset, said to ourselves, we want to get a good value stream for the oxygen. It's no good just venting all of that to atmosphere. You can use it for medical grade use. You can use it for oxyacetylene cutting. Those are great, really high value per kilogram, just not many kilograms required in the scheme of things. So what we found in Northern Ireland was that 30 years of underinvestment in the wastewater treatment plants have meant that most of them, 30 odds, are on full capacity. They're more than full capacity. They're regularly discharging into the water courses, violating their regulated discharge limits, paying fines, not good, but £400 million in the public purse to upgrade the wastewater treatment plants. Well, we can, to some extent, defer or avoid altogether the need for those upgrades by converting the aeration process, secondary treatment, over to oxygenation. And by taking this oxygen and putting it into those dispensers at the works, we were able to show in our testing at Kinniger in Belfast here a 25% increase in the headroom of the wastewater treatment plant. So the big concrete thing at the back here is a sequential batch reactor. That's a big tank full of liquid effluent, which has got a lot of organic load in it. And inside there is an aerobic bacteria eating away at it. And there's rosettes on the bottom with air coming up through, loads of bubbles, and that's what's giving the oxygen to allow the aerobic bacteria to metabolize the material. What we built here is a little version of that, smaller diameter of course, but the same static head. And we ran the tests on exactly the same material, but instead we stepped the oxygen up to sort of 9% additional oxygen to the 21% that's already there, and we got that 25% increase in the headroom. So that's a really good result, and on the strength of that, NI Water have invested in a 1 megawatt demonstrator, which is going to arrive in Belfast the end of February, I think it is now. But this machine, just as a final note, is a very interesting one. It's from CPH2 in Doncaster. As you can see, it's called a membrane-free electrolyzer, and the PEMs, or the alkaline types, which are the more traditional sorts, they use membranes to separate the huge oxygen molecule from the little tiny hydrogen one. It's just like a sieve, really. And the problem with them is that they're very delicate. If you don't treat them right, they can dry out, they can crack. And if you have an unseen leak in a membrane, you can get contamination in the hydrogen tank of oxygen, and then you're getting an explosive situation. And they're also very costly. You have to replace them every 7 to 10 years. The through-life cost of ownership goes up as a result. Membrane-free says, let's not have any. And that's great to save quite a bit of money, and it's safer, but hang on a minute, how do they actually do the separation? And the answer is, in bottom right-hand side there, is a cryogenic distillation plant. So the hydrogen and oxygen are produced on the electrodes as a mixed gas. It's explosive, but you keep it in very small pipes, very short distances, so that if there is an ignition, and it's very easy to ignite hydrogen, then you get a pop rather than a bang. And it's all designed for that. And then immediately you chill this mixture of gases down to cryogenic temperatures. When you get to minus 200 degrees, the oxygen liquefies, but the hydrogen remains as a gas. So then separation is sort of done by gravity, really. And you can take the liquid oxygen and pass it through a counter-flowing heat exchanger to extract the cold energy from it as you bring it back to atmospheric temperature, and in that way the whole cryogenic system can be made to be quite efficient. So that's what we believe is the good technology. We've got a joint venture formed now with CPH2 to open up an assembly plant in Northern Ireland. It would be located maybe at the old F.G. Wilson factory in Larne, or Bombardier in Belfast, or the Michelin plant in Ballymena. It'll employ about 1,000 people, and it would make 2 gigawatts per annum. It means that as a developer of Power-to-X projects, we know we've got the delivery of equipment. We don't have to wait for 2 years. And we know that we can determine the price by the cost of materials, the cost of labour, the license fee, a reasonable profit for the joint venture, and then that's what we pay, not what the world market constraints would dictate. So, we're at this point, in large part actually, in the philosophical and the conceptual design area due to Renewable Engine, and I'd like to thank the whole team for the support that they gave us over those couple of years. Thank you very much.
Not a question, but a comment, which I'm sure you're aware of already. But if you're going full scale with oxygen into wastewater treatment, and particularly into SBRs, an added benefit there is it'll improve the mixing within the SBR, because counterintuitively, a lot of them are square in the first instance, so you can go out to the edges of them. You get rid of dog legs that are there, square tanks. But also it improves the actual mixing within the tank. So I suspect your treatment efficiency will be higher than 25%.
25% is our publicly declared number.
Yeah, I suspect it'll be higher.
I mean, if it's higher, all well and good.
Yeah, it's great.
David, many thanks for that. Very interesting. And seemed to cover a vast area of energy research. There was a lot in there. Just one question then on if we go back to the compressor and the compressed air and the liquid piston, I assume if it can compress air, is there a role for that within the hydrogen economy or as a gas compressor? What would be the advantages over a standard compressor?
Well, it's the heat of compression which you're storing, so the return trip electrical efficiency is much higher. Now, if you're just compressing and never expanding, or at least not in any short space of time, then that model kind of disappears a little bit. Works well for compressed air diurnal. It would be no good for storing energy for a whole year, for instance. And that's again where hydrogen comes in, because the gas consumption is very high in the winter compared to the summer. We do need to have seasonal storage, so that's definitely a hydrogen area rather than compressed air.
But as a compressor, as a compressor technology on a gas compressor.
Yeah, the liquid compressors are one of the preferred technologies for hydrogen compression, actually, because hydrogen being such a small molecule, if you have a piston ring and a cylinder, the tolerances need to be very tight, and it's only a short while that those tolerances disappear because of wear, and then you're leaking lots of hydrogen past the piston rings. If you want to do a piston type arrangement, then Linde have got an ionic liquid piston solution. The alternatives would be to use diaphragms, compression, and or go to liquid hydrogen rather than gases at all. You can pump a liquid easily compared with compressing a gas when it comes to hydrogen.
Could I ask as well, about everything that you're showing there is obviously large scale industry stuff. We have 150 sustainable energy communities going from North and all across the board, down as far as Farrell. We've been doing energy efficiency and we've been doing that for a number of years. We've saved over 50 million in terms of their energy cost. We're moving now to microgeneration. We're looking at small scale local energy independence and security. Would you see a role for this or some of the other technologies you're talking about as part of a matrix of solutions for a small scale local energy generation?
Yes, and if you go back to the very first slide they had there, which is a 33 to 11 kV substation.
Yes.
In Northern Ireland, there's about 70 of those in the rural areas, and in the Republic, it's 250 of them or so.
Well, it is on the eastern side. The western side is exactly what you described there.
Yes, so and when you get that, then the whole genre of microgrids comes along with grid tied microgrids, so you can use the grid when it's available. As soon as it doesn't become available or it's not suitable for you, you can disconnect and become autonomous. And if you're going to have that autonomy, then again, these devices are there to keep the frequency stable and to make sure no one has too much wind or not enough. It's and it is an active ingredient in those models.
Good.
Very good. Thanks, David. There seems to be quite a lot of interest in hydrogen at the minute. I mean, that's certainly what Renewable Engine International Steering Committee concluded. And I should say, as part of sort of their recommendations, we did apply for further funding for hydrogen training. It's called High Skills, so it's a training program to the hydrogen sector, which is of interest. Okay, next up, I'd like to welcome Charlie Farrell from Southwest College. Charlie's research wasn't necessarily aligned with, he didn't have an industry partner per se, Charlie, but it was a very important scope of work, and I suppose it blends kind of recycling. What do we do after we've used all these renewable energy technologies when they start to break down? We have to recycle them. So, Charlie, I'm very interested to hear the outcomes of your research.
Thank you, John. Hello, everyone. For anybody here that doesn't know me or anybody watching online, I'll just introduce myself briefly. So my name is Charlie Farrell, and I am a PhD researcher in the Renewable Engine program. I am predominantly based in Southwest College, and I have done my PhD along with the School of Mechanical and Aerospace Engineering at Queen's. So my research, and the title of the talk today, a bit of a long-winded title, is the physiochemical characterization, kinetic investigation and process modeling of polymers found in end-of-life first-generation PV. So ultimately what I'm trying to do is to look at recycling first-generation PV using delamination methods, which I'll touch on later in the presentation. So, looking at PV modules or solar panels as they're more commonly known, looking at a conventional 60 or 72 cell panel, there's multiple material types, and the material types in the manufacture of the PV module are effectively laminated in a sandwich structure. So we have the aluminium frame, the front glass layer, the EVA encapsulant, which is basically a glue binding the individual layers together, the silicon solar cells, which allows the panel to create electricity, and Tedlar backsheets, which are used to protect the module from weathering effects, and the junction box in order to connect the panels up with connectivity. So my research effectively is looking at delaminating these panels and delaminating the sandwich structure by the removal of the EVA encapsulant. So I'm going to talk a little bit about that later on. However, with my PhD, when you're able to remove the EVA encapsulant in a certain way, you're able to recover some of the other materials that make up the panel. So for example, the silicon solar cells, recovering them in an intact basis where you're able to effectively consider the emissions and the energy requirement in order to manufacture them in the first place. Currently, a lot of the recycling methodologies that are done in industry in Europe by an outfit called PV Cycle are only really looking at recycling the aluminium frame and the glass layer, which constitutes to approximately about 85% of the overall module weight. And then a general module would be about 18 kilos in weight. Next slide, yes. So there's some legislative drivers behind this issue. So the WEEE directive, which is this little logo here in the bottom left-hand corner, you would see that on some laptop batteries and some smartphones. PV modules were added in 2012, and this effectively made it law from 2014 that any supplier or manufacturers of PV modules were responsible for their end-of-life management. So this acted as a legislative driver and also acted as a motivation for the PhD project as a whole. Now, there's an issue with PV modules where when the wattage of the panel, so if a module, for example, is rated at 250 watts at time of manufacture, if it drops below 80% of its initial wattage, it can be classed as end of life. And this is slightly problematic where a panel, say for example, is rated at 250 watts. Once it hits about that 200 watt threshold, it can be technically classed as end of life, even though it's still producing electricity. So the PV module lifespans are approximately 20 to 25 years, and that's indicated by manufacturer guarantee. And then the diagram I have up in the top left here is the waste management hierarchy system. So if you can click twice, Yasi, there should be two. Yeah. So obviously the most preferred method is the prevention and minimization of this waste at the top of the hierarchy. But currently where the PV recycling industry is in around here, where you have recycling and potential energy recovery, which I'll talk about later. Next slide, please. So another driver with the recycling of these modules was a report published by the International Renewable Energy Association in 2016, where they indicated that by 2050 there would approximately be 60 to 78 million tons of PV waste. Now, with the exponential increase and annually in PV module, the exponential annual increase in PV module installations, this number is expected to rise as well. And then a little diagram here put down at the bottom is from the Fraunhofer report, which shows the market share of PV technology. So my research is only looking at first generation PV modules, which dominates the market share here. So the two different shades of blue is first generation PV, and the green you've got second generation, which is thin film technology. There is a third generation in PV technology, however, it's yet to reach the industry market. And as I mentioned there, the first generation PV technology, which is known as crystalline silicon, hence the CSI abbreviation here, dominates between 80 to 90%, and that graph down at the bottom there shows a 36-year period between 1980 and 2016 where the market is predominantly dominated by first generation PV. Next slide, please. So with my research looking at the breakdown of the encapsulant layers and the encapsulant polymers in PV, back in the first or the second slide where we saw the design, the encapsulant polymer sits both top and bottom of the solar cells in the module. So there's two layers or sheets of EVA used to encapsulate solar cells. It's been proven in literature that it's the most difficult step to recycle PV modules. And in industry, it's been used as the primary encapsulant since the early 1980s. Now the solar grade EVA generally contains about 33% vinyl acetate content. And vinyl acetate is this little section of the polymer here that's outlined in red. It's been used in industry primarily due to its excellent transparent properties and the adhesion properties to be able to act as an adhesive between the front glass layer and the back sheets. Next slide, please. So my project effectively was split up into 3 work packages. However, there is 4 sort of discrete studies that make up my PhD. So there was significant gaps in the knowledge. When I started the PhD, there was very little research regarding PV recycling. There had been a bit of a boom in the early 2000s looking at the area, but then it completely dropped off up until the point where it had been added to the WEEE directive, and then that obviously increased with the research publications in that area, as it was a motivation again for my PhD as well. So the project was effectively outlined in 3 work packages, looking at the characterization of the polymers used in the PV modules, both the encapsulant and the backsheet polymer, kinetic modeling, as well, which is looking at a phenomena called the kinetic triplet, where you have figures on the rate of reaction or rate of decomposition of the material, the pre-exponential constant, and the actual energy required in order to initiate the reaction to break down the encapsulant layer. And as I mentioned, there was 4 sort of discrete studies. The second work package on the kinetics was split into 2 studies, one looking at the encapsulant polymer and another one looking specifically at the backsheet polymer. And again, work package 1 and 2 was used as inputs and prerequisites for the process modelling of work package 3. So looking at some of the thermal studies of the encapsulant polymer, it tends to degrade in 2 stages. So there's a graph here looking at 2 different samples from a publication from the PhD. So here we've got the used encapsulant used in a PV module, and then here we happen to have the virgin grade encapsulant. So you can see the trend is the same, and the peaks and the actual positioning of the decomposition temperatures are quite similar as well, looking at them 2 samples. So what this has told us is that potentially the decomposition stage of that polymer can be split into 2 discrete steps, and then this also translates looking at the activation energy of that polymer, where there's 2 reactions going on, where you have a discrete number or discrete activation energy for the first stage of decomposition, and then another figure for the second stage of decomposition. Now, looking at the graph here, you've got the percentage weight loss of the material, and the green curve here, you can see it goes down to near 0. So what we found by doing numerous thermal analysis at Queen's University is that after the module is pyrolyzed, there's about 1% residual material left over. So in terms of conversion, it's quite a clean conversion as well. And then using the technology of pyrolysis, it means that there's no oxidation in the other materials that are left over once you have delaminated the sandwich structure effectively. And then this particular technology targets the energy recovery section in the waste management hierarchy, which I've mentioned previously. Also, it also considers the emissions relating to silicon production and the use of hazard chemicals for reprocessing. So when the modules are recycled in industry, they're broken down and crushed and milled, and in order to reuse that silicon again, you have to employ the use of hazardous chemicals to remove some of the layers in the silicon cell. Then it has to be further melted, made into an ingot, and then there's energy also required to saw the ingot into discrete solar cells or silicon wafers. Another part of my work looked at the energy inherent in our waste. So looking at the used and virgin grade encapsulants, looking at gross calorific values. So the energy content for the used and virgin grade encapsulant, the figures were almost negligible, about 0.4, 0.5 megajoules per kilogram difference. And with the energy content of that encapsulant, it's very high and comparable to that of biodiesel or heating oil, which is 40.2 megajoules per kilogram and 42.6 respectively. Next slide, Yossi. So here, if you click twice, there should be 2, yeah. So here I've developed a diagram. Basically, it's a butterfly diagram that was made famous by the Ellen MacArthur Foundation, looking at circular economy concepts a few years ago. We've developed it looking at the overall lifespan of a PV module. So looking from the mining and extraction of raw materials stage through to the manufacturing of silicon wafers on the actual module, the module lifespan and usage, and then potential end-of-life treatment. So currently where we are looking at like initiatives like PV Cycle in Europe, we're here where we feed back into the chain, sort of the first cascade, C1 here, where it's recycled. It's basically crushed down and milled down, as I explained previously, and it has to go right back to the start of the process, where the ideal circular concept would be that you'd want to repair or maintain these modules. So there's a debate there with regards to eco-design as well, and how these modules are designed, because the design hasn't really changed throughout their entire lifespan, and in terms of the materials used as well, they haven't really, the ratio of materials has changed, but the actual materials themselves haven't really changed for the entire lifespan. So yeah, this again explains the circular concepts and potential cascading options where you could look at, for example, remanufacture, reuse, redistribution, and repair and maintenance. So at the moment, most of the modules that aren't recycled, if they're outside of Europe, they're sent to landfill, which is problematic. So if you click on to the next slide, you can see this is sort of the reality of where we're sitting. So this was a few years ago, published in a report, and again, modules put up in landfill and end-of-life modules. What ultimately we have to do is to look at the end-of-life stage and potentially look at some eco-design arguments as to how they're designed and how they can be effectively maintained and potentially redistributed throughout the network. So if you click the next slide. So just on a last note, I've included here some links to some of the open access publications that was published as part of the PhD project. So there's 2 publications there. The top one, Technical Challenges and Opportunities in Realising a Circular Economy for Waste Photovoltaic Modules. That was published alongside some of our colleagues in IT Sligo. And again, the kinetic modelling paper for the EVA encapsulant was published with some of our colleagues in IT Sligo as well. And then the assessment of the energy recovery potential, which is effectively the characterization study outlined in Work Package 1. That was the first publication from the PhD that was done alongside some of the links at Southeast University in Nanjing in China, where I spent a bit of time as part of the E9 partnership program, as part of the PhD. And I've just left there in the bottom right hand corner a little QR code if anyone's interested to take a look at some other bodies of work. So this is open access publications, so anybody can click onto this and read this. And that's it. Thank you. Any questions? No.
You covered it all, Charlie. You covered it all.
Right.
Thanks, Charlie. Got away lightly there. Okay. So next up, so to just put down that big one, yeah. Just want to take a wee bit of time, just I suppose look at highlights, some of the highlights for Renewable Engine project program. Maybe give you a wee bit of an insight into, we did a final video. It's not released yet, so can't show it all, I don't think, but we'll maybe show a few wee bits and clips where we're at. I suppose this is the sort of pat in the back stage for Renewable Engine. We don't like patting ourselves in the back too much, certainly in Northern Ireland. And I think it's important to show sort of some highlights. Told Ashley to make this famous. There's a main video there. Yazzie, do you want to play it? I think it's about IT Sligo, so it's basically some clips just from the end final video.
So the area we are currently working is mainly on sustainability and advanced manufacturing process. And a company and a small and medium scale company is working with us. The technology we have used in this project is called photocatalytic technology for hydrogen production and also for making these materials for antimicrobial applications. So same material or same technology has two different applications. Photocatalytic hydrogen production is a way of storing solar energy into chemical energy. This is an exciting opportunity to work for us in the program.
That's it.
There might be another one there. Sure. Well, why do you look for that?
Which of the other ones?
There should be a longer one there.
Okay.
But I suppose a couple of points just to highlight, and I suppose this is kind of from the start of Renewable Engine. Charlie mentioned there his trip to China. It's that long ago, I totally forgot about that. That's kind of pre-COVID. I suppose the world we live in now is kind of what happened before COVID and then what's happened since then. But it's been going 4 years, hasn't it? Is it 4 years probably now? 4 or 5 years. So here's what we've achieved in that time frame. So industry grants, 5 companies supported with grant awards, a combined value of over 450,000 euro. The program's delivered 5 new products, prototypes, 2 new processes developed for hydrogen, solar, offshore wind, and energy storage sectors. On July last year, Renewable Engine successfully completed a combined target, delivering 58 research years. So I think that in itself is some achievement. When you start these projects out, you write the ambitions. When you get the award, you realise, oh, what are we committed to here? But I'm pleased to say, through the hard work of all the partners, that we've successfully delivered on all our targets. And that's, be congratulated. It's through really hard effort from everybody in this room and taking part online. So I think, congratulations. In recognition of the hard work of Renewable Engine in November there 2021, Renewable Engine was awarded winners of Research with Impact category in the highly prestigious UK and Ireland Green Gown Awards. And again, that is some achievement. That's basically across all the education sector in the UK. There is a worldwide one as well, but it's really, I think the numbers are about 180,000 students and thousands of academic researchers. And Renewable Engine were awarded winners in Research with Impact. And so that sort of goes to tell you the level of world-class research that we are participating in. Sometimes you get into your own silo. It's maybe a appropriate word for anaerobic digestion technologies, but and even the Kingspan. But when you come to the events like this, then you realise, okay, look at all the work that's been achieved in the last 4 years, and then maybe when we come together, that's when we realise that there's actually been a lot of effort by a lot of people here. Looking at the presentations there today, to be commended. Just some more stats for you. Partners collectively delivered over 30 open access publications. That's on the repository, thanks to Alistair, on the website. And again, that's for public consumption, if they're that way inclined. And we've collaborated together across UK and Ireland for just 10 cross-border high-quality research publications, and many of them within the top 25% of research. So again, well done to everybody. Student engagement. I mean, that was a focus, and John, you mentioned earlier there about for this male-dominated sector, really for manufacturing, engineering is traditionally male-dominated. We had over 50% of our researchers being female, and we had over 8 different nationalities represented across the programme. I'm sure that no other project has achieved that. That's just fantastic. Some more things really. Sean presented his work with organic power. It's part of the research undertaken at IT Sligo. So congratulations, Sean was recognised as he received the Environmental Science Association of Ireland Award for Postgraduate Research of the Year in 2020. So these are the things that we would like to celebrate. Congratulations to Sean. That's all I have, but I think that says it all really, that there's been a lot of effort, a lot of hard work, and really from the presentations here today we can see where the academic research linked into industry can take us. We can take it out of theoretical and try and make growth opportunities for everybody. So I think that's what we set out to do, and I'm proud to think that we've achieved that.
Which of the videos?
Version 3.2 there is a larger video.
Yeah. So go.
Try that one, Jose. So my video editing skills might not be.
So the area we are currently working is mainly on sustainability and advanced manufacturing process. And a company and a small and medium scale company is working with us. The technology we have used in this project is called Photocatalytic technology for hydrogen production, and also for making these materials for antimicrobial applications. So same material or same technology has 2 different applications. Photocatalytic hydrogen production is a way of storing solar energy into chemical energy. This is an exciting opportunity to work for us in the program.
My name is John Bartlett, and I'm involved in the Renewable Engine project in 2 capacities. The first is as an environmental scientist and a principal investigator. I'm a supervisor of a PhD in small-scale anaerobic digestion in farms, and a co-supervisor in a project on energy generation. As head of research for the Institute, I'm involved in representing the Institute initially in putting the consortium together, and then taking part in terms of providing facilities that you see here from the Institute, and in providing expertise into the overall management group and the international steering group as well. There are 2 very important aspects to the future of the Renewable Engine partnership. The first is that the model of engagement for industry, where we've seen industry taking in PhDs for the first time and developing their capacity and their ambition for research, that model will be extended much deeper into the economy and indeed into society in the partner areas. Second one is that the partnership itself would be deepened and the scope would be significantly widened, and that the partners that we have, along with others, would do much more collaboration into the long-term future.
Myself is Sneha Matthew. I'm one of the PhD students here in IT Sligo in Renewable Engine program. Through Renewable Engine programs, I'm working in collaboration with our industry partner Castus. It's based in Dublin. So my role is to develop material that is light active and to use for antimicrobial application, as well as to produce hydrogen from water. In addition to this, we were able to communicate our technology to the readers, to the public, by publishing more than 9 publications in high impact journals, as well as collaborating within the Renewable Engine program with other collaborators.
I'm Paul Blackwell. I'm the principal investigator here at the University of Strathclyde on the Renewable Engine project. We've worked with a variety of companies as part of the work we've done over the last few years. One was a startup, the second one was an SME, and the third a slightly larger engineering company. The startup, a company called Soltropy, was looking at the development of a solar thermal heating system which was intended mainly for domestic purposes. And we worked with the lead researcher there to develop that product to the stage where we've now got a working prototype actually situated on a roof that can be used for examination of different storage media within the thermal storage system.
Hello, my name is Charlie Farrell and I'm a PhD researcher on the Renewable Engine program. My work focuses on the thermal delamination of end-of-life solar photovoltaic modules. The impact of my PhD research was we were able to look at 3 discrete areas looking at the recycling of photovoltaic panels, which resulted in 3 cross-border publications of my PhD work and a book chapter. Currently, I'm coming to the end of my PhD. However, this is not the end. We hope that my PhD research can be used in funding applications to help address sustainability issues and also to look at the UN Sustainable Development Goals.
Pat Cassidy is my name, Managing Director of Platinum Tanks Limited. We're based in Lochaigish, Castlevania, County Monaghan, and we're here this morning, so we are just to do a little bit of a run on a program that we took part in, a renewable engine program, which was in conjunction with Southwest College in Cookstown and our academic partners were Queen's University. Currently our core business is manufacturing containers to hold fossil fuels, namely kerosene or diesel. And on the back of developing the solar panel stand from recyclable plastic material, it allows us to diversify into new markets, because in the next 20 years the use of fossil fuels as a means of heating and everything else is going to be non-existent. So we have to diversify our business into markets where there's going to be a viable future.
Very good. I think it was important to show that. That's, you know, from clips from people that couldn't join us today. Hopefully they're online. But it tells each tells a different story. You know what it means, what people's participation in the program was, why they participated, and, you know, hopefully what they've got out of it. So there's some exciting products there, and some great learning. So yeah, fantastic. I think next up we've got 2 more events, I think, scheduled. So we have Ellie Smith from the University of Strathclyde. Again, that's pre-recorded. And what's the final thing then? So we're going to have a round table on future directions. So while we have you all here, the main question is, if we were to start at a blank page, knowing what we know now, what does Renewable Engine 2 look like? So we'll cover that off, and then we'll draw to a conclusion. So we'll hand over to Ellie.
Hi, my name is Ellie. I'm sorry I couldn't join you live at the event today, but in any case, I would like to say a little bit about my PhD project, but more importantly, I'd like to demo some of the technology that I've been working on as part of that. Interesting and enjoyable for you all. So a little bit of background on my project first. I'm one of the Renewable Engine PhD students. I was based at the University of Strathclyde and worked alongside my supervisors Paul and Dorothy. I also had my industrial partner for support, which is Boothwelsh, an engineering services company who have a real interest in Industry 4.0, and especially augmented reality. And that was really great because my project was looking into how augmented reality can be used to assist operators in maintenance activities in offshore wind, but also in the engineering industry more widely. And it's augmented reality that I want to give you a little bit of a demonstration of today. First things first, what is augmented reality? So the easiest way to understand it is if you imagine a spectrum with the real environment on one end, that's just the world as you see it around you today, and on the other end is the virtual environment, so this is a fully computer-generated world So think computer simulations, virtual reality, Oculus Rift headsets, all those kinds of things. Then between those two extremes, we have another range of technology. There's augmented virtuality, which I won't go into today, and there's what my project focuses on, which is augmented reality, or AR. And that is where we retain our view of the real world, so we've got that live sense of what's happening around us, but it is overlaid or supplemented with additional digital information. So that might be CAD models, that could be animations, it could be a live stream of data from your IoT sensors, and it could be anything like that. So it's a really useful way of blending the digital and the physical, and that can be really useful in industry, especially because you've still got that live view of your surroundings, so that you have an awareness of the hazards around you, which is an advantage it has over virtual reality, where you're totally cut off from the real world around you. So the target of offshore wind was selected initially, and we think AR has promise here. So offshore wind turbines are large, complex machinery, and there's a large opportunity cost if those are down and they're not producing energy. Because it's difficult and expensive and dangerous to access them, it means that when we do send somebody out to do maintenance, whether that's reactive or preventative, we want to make sure they have everything they need to be able to do that job and get it right first time, so we can get that asset up and running again. And we believe that augmented reality has the potential to help with that by providing data right at the point of use to reduce downtime and therefore reduce operation and maintenance costs. So as part of my research, we needed to develop an AR application to display those instructions, and the technology we chose was web-based augmented reality, which gave us a very flexible solution. So this uses the same basic tools as any website would, that's JavaScript, HTML, and CSS, but we use some additional special JavaScript libraries which enabled us to manipulate 3D content within sort of the video stream of the camera on the device that you're using. And as I said, it gives us a very flexible solution that was easy to sort of chop and change, manipulate different user interaction factors, which was useful in experiments. But the other really important thing about using a web-based approach is that it allows us to come up with a device-agnostic solution. That means it's a solution that can be displayed on a range of devices. So anything really that has a modern web browser and a camera, you can use these kinds of AR apps on them. And that's really useful, both for research purposes and in the real world, I think. So some of the experiments we were doing using these web-based apps, we did some tabletop experiments where we manipulated different factors in the user interface to see how that affected performance. We also did some experiments to see how the effects of novelty and learning impacted performance. So do people get better with practice, or does the novelty of the new technology wear off and they start to drift a little bit? We investigated a couple of different applications where we saw this being applied as well, including a sort of vocational training tool, sort of supplement physical access to training materials. Could AR be used as a digital kind of helper in those situations? And we also looked at it in the context of on-the-job training for spatial tasks such as programming a robot arm, and we had some success there as well. And so it's time for a demonstration. But on to the more exciting part. And so it's time for a demonstration. And so if you want to grab your phones and scan this QR code, if you you don't have a QR code reader, you can visit the website on screen. That's my GitHub page where the content is hosted. So while you're doing that, I'll just give you a little bit of an explanation.
So I'll just wait while you scan that for a second. Okay. Okay.
This is using those web technologies that I mentioned earlier, and this is a small piece of work I did in collaboration with Southwest College to model a electrolyzer for a hydrogen fuel cell. And so if you've got that page up and running, I'm going on to the next slide now, but there'll still be a QR code there if anybody's still looking for it. And if you visit that page, you should see something that looks a little bit like this. So you can see that 3D model exploded view of the components. And if you tap the view in your spacebar, you'll need a flat surface nearby. And so as the instructions on the screen say, just point your phone down, looking at an empty space and move it around. That just lets the sensors in your phone detect where a flat surface is so it knows where to place the object. And you can then use 2 fingers to pinch zoom, rotate, or 1 finger to move it around if you want it in a different place. And then you can really just get up close and personal, walk around it, move closer, move further away, and you can see how this can be quite an intuitive way of interacting with 3D models, and that is one of the advantages of augmented reality. So I will leave you that, and I'll leave that QR code on screen just in case anybody still needs it. But just to say thank you all for listening, and thank you to Southwest College for organising the event, and I hope you enjoy the rest of the day. Bye-bye.
Oh, thanks, Ellie, for that. I was too busy playing with the model there. Yeah, no, very good. I think that shows the power of kind of modern technology, what you can do with it. I opened up that, and then you have a model of a fuel cell. It's in the palm of your hand. Fantastic. Okay, just I suppose really just to wrap up, and this is then more of a conversation. I think we have a slide maybe on it, Yazzie, do we?
Is that in your presentation?
Yeah, it's towards the end. And this can be as short as long as we decide. And I'm not sure if I don't know if there's online, you can get engagement online, sure, ping through any questions or comments you have at this point. Might be useful, and comments on the presentation. We can pick them up. So I suppose the first question was, if we're starting with a blank page, and given what you've heard this morning and where we started, absolutely a lot of successes. So maybe one thing that was good about the program, or what you thought was the best element. There are pain points, certain pain points. As I say, a lot of it is perspiration, certainly trying to get the thing wrapped up in the last few months. I think the finance team will agree. It's been a lot of perspiration after, but it's getting that balance. So maybe it's probably best maybe we go round each table or have a brief discussion about what you thought was the best thing about Renewable Engine for you personally. Something maybe that we could do better next time. So if we're going to design Renewable Engine 2, what should that look like? Should it be more industry? Should it be more collaboration? How should that operate? From a student's perspective, should the student be out more with the company? And we had the balance there, but so it's just that kind of conversation.
If I could make a comment maybe, John, and it's following on from the sorry, back to people, apologies. It's following on from my earlier comments on the arc from 40 years ago to today.
Yeah.
And the growing realization at both government and societal level that the response to the climate crisis, if we can use that term as poor enough as it is one that obviously is multifactorial and multi-layered, but also it's multidisciplinary. It crosses all sectors. You know, it's not the bailiwick of any one group, government or society or whatever. It's literally all of us working together. Not wanting to use the COVID term, but you know where I'm coming from. And one thing I would say about Crest first and then Renewable Engine is that we have proven a model of collaboration and engagement that others are only starting to think about now. About how do you solve the real code-based problems in first instance, and then how do you build capacity in all those layers, companies, society groups, government agencies themselves, so that they're thinking better about what the ultimate solution is likely to be. So for me, that's the power of it. And I said earlier, you know, this is by no means an end to anything. It's the next step to what I confidently predict will be a number of other collaborations with the Northern Irish and Scottish partners and others. So, I don't know if Peter, would you agree with that? Or?
Yeah, I do. I think for me the important thing is the industry connection to the research. We do a lot of work in the universities, which is great, but we miss out, I think, in seeing how that might develop into a product or into something that really has an impact. I think renewable engine has been very important in providing that connection. I think it was also good that there was closeness with industry, but it wasn't too close as well, because sometimes we've had projects that are too driven by industry, and I think in this one we got it about right. It was a connection, and both parties were involved, but there was also a bit of a distance to give the researchers time. I do think COVID affected us badly. I would have liked to have seen students more integrated with the companies, and I was really looking forward at the end, maybe the final year, that the guys would have went and spent much more time with the companies. I think that would have been beneficial to the industry, but also to the students themselves to get that experience. So I'm sorry that didn't happen.
I know what you mean by too close. I had a relative last year was considered buying the house next door. We are close, but maybe that's too close. Chris, what do you think of the comments from the academic side? If I go now to the industry and say, right, well, what does industry think?
I mean, I think to be fair, our project was maybe a little different to other people's because we had change of personnel and I was not involved at the beginning, so we've had some communication issues and so that's made it challenging for all parties. I think Sharon's probably going to kill us at some point, so that's probably fair. But I think we did strike a good balance. I do think at certain points, I take this comment of industry work to move different timescales, but sometimes that is necessary to get things. Otherwise, you will miss out, and I think that's where trying to strike the right balance can be hard.
Would it be fair to say that sometime in the academic world we must say plod along, but we go at a very steady pace, and in industry, as you say, change personnel or change of priorities in the company, and suddenly it's urgent or it's not urgent, and then it's right. I need that yesterday.
I think as well sometimes it's striking the balance between knowledge building, which I've been Charlie's shoes. I've done my PhD, and sometimes knowledge building isn't solving the coalface problem. The coalface problem is the coalface problem. It just needs to be solved, and sometimes you need to make sure you don't go off on tangents. You're maybe not building as much knowledge as you'd like, but it is just honing in on that problem. So I think Alex, for ourselves, my experience with Alex, we've done that, and we've got to the point led by push that on. So any review of that would be good from our side.
Well, I'll pick up with Alex then, Alex, from your perspective, or from a student perspective. Do you think the industry engagement's vital, crucial, nice to have, or a distraction? All of the above?
It's nice. It's been nice to suddenly be able to apply. The original project was on development of foam structures. The rotational molding industry as a whole is not particularly keen on developing foam structures at this moment in time because they're quite complicated to make. They take a long time to be able to cool down, so they're expensive to run on machines. But taking what I learned from that and applying that to the hydrogen project, it gave me that nice link between, okay, this stuff might not be applied in industry for the next 10 to 15 years, but here's a direct application of that research that can happen right now that I wouldn't have got without the link with Kingston.
Yeah. Anybody else want to make a comment? Okay. We won't wrap up. What we'll do is take 2 minutes at each table. I don't think most people do work like that. Okay. How else is Renewable Engine 2 going to get written? One point that you thought would work best, like just one sentence, and what didn't work. Because what didn't work is probably as important as, I'm not saying didn't work, let's just say was difficult, and how did we change that? Is that fair?
Yeah, so what I could, just to add to that, what I could advise we could do just so that it goes in the notes. There are notepads on each table, so as a table, if we could just write it down on those sheets, and then, yeah, so no need to label the table, so then I can go around and collect. And
the added bonus, because John's looked at me going, did we not just cover that? Is if you have the collaboration and you just get one person to report back, well, they don't have to take responsibility and send the other stuff in, so they can blame the others at the table.
Okay.
Sure, I would just do bubble back and then.
Yep. Because it's actually launched 12:30, so it should be good to go.
My question was to do with somebody like Alex provide solutions. Because we're looking now to change the way I think that's probably where I picked up the values of Alex was very engaged in it, and then my challenge to them is to change
Fourth person to lead the
That wasn't necessarily
Okay, just like your launch truck, is it trunk here for you, okay?
Each project to get the
Well, if you check our one, digestion, Sean worked with organic power all the way through. But he had to do his PhD separate. Yeah. But no, we could have integrated very well. It's just an organic power themselves. So there wasn't a unit juice that we could test. So we had to separate them. Exactly the same. There's plan A and plan B. So we run the board at the same time. And if plan A works, that's good. If not, then the PhD.
I remember very well I don't know why industry renewable so you had to sort of develop the PhD work and how we develop what the technology was, then the industry projects came in as a way of taking it and doing something with it. They were very keen to have industry projects earlier. There's two brands.
Right, how are we getting on? Have we got a spokesperson for each table or?
Not taking notes. Yep.
Yep. Are people online? Yes. Can they comment or no?
No.
Yeah, they should be able to.
Maybe
no one is. Sorry?
Probably all.
Yeah.
It's just 5 on now.
5 on now.
Yeah.
It's been dropping on now.
It's dropping. Yeah. I think because we started doing the in-house session, then they started dropping off. But we're about closing now. So I get them.
So the conversation's
going well. Yeah. It's not bad. Okay.
People's lunch ready?
Yep. Yeah. It's all out there already. Yeah.
Okay, so I have told lunch is ready. If that doesn't convince you, the discussion must be going really well there. We'll start with it. I suppose the purpose of this is just so everybody can get here. There's an opportunity to say your piece. We're going to apply for new funding. Well, what should that look like? John, do you? I don't know who wants to be.
You said whoever writes it down doesn't have to speak.
Actually, that is usually the rule, isn't it? Who's ever described. So we pick one of your two. One good thing, one bad thing, or not bad thing. What would you do?
It's really what we were saying previously. You know, the engagement model is a good one.
It's good, isn't it? Yeah.
And certainly the flexibility that is and was in the program in terms of, you know, normally PhDs would have a fixed shape and you'd start at the start and you'd finish at the finish. But we needed to be fleet of foot in the middle, and we were fleet of foot in the middle, so that was good. On the difficulty side, communications, which is always an issue. But in terms of, like, if we're going forward again, that industry would be clear at the design stage of the projects what communications they need, so that we're clear and that we can deliver it from that point of view. And then the oldest one of all, balancing academic and industry timescales, which they do work in very different ways. So, but I think we're conscious of that. We just need to be more explicit about it.
How would you solve that problem? Is it more of a looking at you, Chris?
Why look at me? It wasn't me.
You look at me. I mean, maybe it's a blended approach, is it? You know, you PhDs, there's master's projects that can come in as that or something.
Peter was making the point about the project within the project.
Yeah, I remember, John, when we were discussing the industry projects, that I initially had this thought that we would do a certain amount of research for a year or two, and then the industry projects would kick in almost as an extension of that. But in the end, we sort of had them almost separately produced. There was a call for industry projects that could be linked obviously to the PhDs, but weren't necessarily the same thing. So you ended up getting bits from companies for something that they wanted on a short time scale. Where the project is this longer time scale. Certainly, what we ended up doing with Keenspan wasn't really Alex's PhD. It was something else. But as Alex said, it built into that.
So it's maybe bringing that, being more explicit there, because I think we didn't really look. It's a balance. If I look to the finance, they'll go, well, or some others will go, whoa. Thankfully, it was 3 years because it took us that long to get the, So.
No, we achieved a lot in the end, but if you were being critical, you might say it could have been a nice carrot for the industry engagement in the beginning to sort of say, look, we'll develop this research. If you have a close relationship with the researchers, then we'll reward you with this actual funding then to turn it into a product. So we sort of did that in a number of cases, I think, in the end, which was good.
It's useful. There's definitely something in there just to kind of get a better structure around that.
Yeah, you can over-organize it too. If it becomes very rigid, then it will not work. The flexibility that John was talking about, that's a positive thing.
As we do.
Ashley, what about yourselves at your table?
Well, personally, I think the team worked very well, and when colleagues get on, it's so much easier. Like myself and Mark obviously worked in the other applications, and then myself and Mark in housing, so it just makes the whole process easier. What I felt bad for probably during COVID though, again, the students maybe didn't get together, or we couldn't share their woes, that maybe would support them. So I think more interaction with the students, for the students, would be great. Just to help them along.
I think we recognise that probably as well. It's kind of don't want to interfere too much, but maybe from the student table, what would you change then?
Change in that particular instance?
Well, no, say if you were redesigning Renewable Engine 2, what worked well and what didn't work well? I suppose as Ashley said, okay, there communication, or was there something that we could have done differently to get that engagement?
Well, on the good side of things, the way that the project was established under within Queen's, like all of us have been exposed to multiple different areas of engineering. I come from a design background, but I've been wiring robots. I don't have a degree in electronics, and I don't know the first thing about it, but it's exposed me to that. The other side of the coin is that there seemed to be a mismatch between the funding requirements, which really held back the project at the start. We were having to produce quite a lot of paperwork just to buy simple things. But in some cases it's unavoidable.
Yeah, welcome to our team. It is. I mean, one of our recommendations certainly on the funding side would be that we would probably try. We can't do it as kind of public sector funded organisations, but we did try and minimise the exposure for companies to that. It's tricky. So I think in the future we would have a more of a tender process where it would be a competitive, and they would bid for an innovation piece of work rather than apply for a grant. I think that would work better. So we'd probably address that. Doesn't help the student unless, of course, you can get that the company to buy the equipment based on their process.
But I think that is part of that mismatch between things happening in the industry, where if you need something, you can buy it right away.
Yeah.
In academia, that doesn't happen. There's about 20 different forms to fill in before you get to something.
Okay, no, well, duly noted. I mean, these are things. I don't know if we can solve some of those, but it's important to know how we can try and get around them. So that covers your yeah. Charlie, do you want to give a few points? Only yourself and David, so we be able to guess who said what.
No, well, we have just briefly talked there. So something that I put down here that worked well. It actually sort of stemming back to one of the earlier renewable energy videos. Ali had made a point about going into a project that industry has asked for specifically. So the actual structuring of the projects from the companies, the fact that it was like an industry pitch, if you like, to the renewable energy partners, that seemed to be a very good aspect because all the students that had company involvement, they all seemed to like the project effectively and how it developed. I suppose that also then stems in what Ali said, that it provides relevance, sense of purpose, and sort of really application of the projects as a whole. And then there's a few other things there that just overlap with what Alex had mentioned, exposure to other types of industries, sort of that multidisciplinary approach.
So do you think that sets you up then if you're coming out of a program like Renewable Engine rather than a PhD that you express that if you're going for an interview or you're going on to your next place? That experience is valuable, I guess.
It gives you numerous opportunities to discuss transferable skills in an interview.
I'm going to take that as a good point. Yeah.
Yeah, and I suppose the other thing there, just with maybe what the change would be maybe with regards to, I know obviously COVID and everything happened, but the intention for I suppose more blended time, I suppose on a monthly basis between the universities, the industries, and partners, potentially partner institutions as well. I know that we met every 6 or 9 months with the other institutions, the academic partners anyway, but there's no reason I suppose why there couldn't be more more put in there maybe on like a 6-monthly or yearly basis where for example, let's just say I know we brought in like elements of let's say training and workshops when we were over at Strathclyde or at IT Sligo, but there's no reason why I don't think you could factor in some other workshops or activities that might potentially benefit the students and subsequently might benefit with regards to the information provided, maybe some of the industrial supervisors as well, or something to feed back into that chain.
Well, here, but one final question then. On the student side, do you think we interfere too much or not enough? So you have to balance your kind of research with all these events, and we were aware of that. I know, how many events do you get them to participate in? when they're trying to actually complete their thesis. Did we get it right or not?
From my point of view, I think it was just, but I think we could have been more efficient helping each other. What I mean by this is, at least personally, I struggled during my research in several moments in which probably, I don't know, maybe going to the industry or talking to some different maybe other students or maybe yourself or some other people in the project could have benefited me in developing maybe the research path or making decisions alongside the research or things like that. That's just essentially my point of view. But however, me personally, I subestimated the time that everything was taken, and I think everybody that knows me very well and knows my path can agree with me in this. But I think even though maybe timescales weren't as adequate as I personally probably would have preferred, I think it's still the outcome of the research in every single project. I think it's been very, very impressive. Very, at least from my point of view. Just seeing, for example, Ellie's project there or Charlie's there, it's been very, very impressive. And seeing also Alex collaboration with Kingsman and that molding and the outcome, I think very impressive. I think. We haven't even talked about, for example, the energy saving that potentially the robot can provide to the industry when we implement it.
But I think that's useful to finish off on, David. That's probably why these events are useful. I think everybody underestimates how others view their research. You know, you get involved in it, you do it, but you know, don't shout about it. Until you see these events, you go, everybody else is looking, everybody else going, oh, that's pretty good, that's impressive, that's, you know, and through these events then you can see that. So, look, we'll not hold you back. Congratulations everyone. I think today has highlighted just how impressive that is. Everybody's done a great job. So, pat yourselves on the back. Let's go to lunch. Where is lunch, by the way?
Not in this hotel, John.
Definitely not skipping lunch.